Welcome back to a course on limits and continuity. In this lecture, we'll start with the definition of a uniform continuous function. So let us start it formally. A function. Here also we are going to talk about a function that is defined from x to y. Okay. Whenever we say a function is defined from x to y, here in the context of analysis, we have to be very careful that these two sets x and y are metric spaces with respective metrics. Let us denote them as dx and dy. That's it. Okay. This function is said to be uniformly continuous. If for every epsilon positive there exists a delta positive such that dy of dy of f of x comma f of y less than epsilon whenever dx of x comma y less than delta. This is true for all x and y in x and y in x, right? If you want, you can restrict your domain to be a subset of x as well. That is also permissible. A function is said to be uniformly continuous if these things happen. Even in the definition of continuity, we have spoken about epsilon and delta. Here also we are talking about the same things. Are there any differences? Yes, of course there are differences. And that is why we have two different notions of continuity, that is continuous function and uniformly continuous. The first thing, in continuous definition, in continuous functions, we define the continuity at a point. Okay, whereas the uniform continuity is defined on a particular set x. Okay, at a point, whereas uniform continuity is defined on a set. If whenever we are talking about a set, it means in all the points of a set. That has to be that, right? Okay, we define the continuity of a function on a set as well. In that sense, we talk it is continuous on all the points of a set. Okay, and in both the cases, we fix epsilon. Okay, we choose some arbitrary epsilon, positive quantity. In continuous functions, epsilon is chosen based on delta is chosen based on epsilon and a point of continuity. So the point at which we speak the concept of continuity also takes place in the definition of continuous functions, right? In uniform continuous functions, delta is chosen only based on epsilon, because we are talking about all the points, so no point should be involved in the choice of delta. If we are able to do these things, then uniform continuity can be established, right? Next, I would like to make some remarks as results here. That is, first one, uniform continuity implies continuity. If suppose a function f from x to y is uniformly continuous in the sense that function is also continuous at all points of x, whereas the converse need not be true. If we talk about the real functions that is different from the set of real numbers or the subset of real numbers, there we have a special result, a function which is continuous on closed intervals. So on closed intervals we are specifying, which means the domain must be a closed interval, right? A function which is continuous on closed intervals are also uniform continuous on the same interval, right? Now let us explore few problems on these things. After this we'll come back and do the theorem proof. So the first problem that we are going to do is f of x is 1 upon x. The interval that we consider is open at 1, closed at 0. So this is the interval that we have considered, and we are going to check the uniform continuity of this function. If this function has to be uniformly continuous, we will have to identify a delta based on epsilon. So first let us fix epsilon positive. Okay, we will have to identify some delta which is independent of the point but is depend upon only epsilon, right? So the ultimate result that we would like to get is what? F of x minus f of c, and this c may be any value, right? I choose c may be any value. Instead of writing this as y, I am writing this as c. So nothing wrong in this. This has to be less than epsilon whenever x minus c is less than delta. So this is what we would like to prove. Okay. So this may be written as 1 upon x minus 1 upon c less than epsilon, and this is nothing but this is nothing but c minus x upon cx less than epsilon. Okay. If this is the case, this may be split as minus delta less than x minus c less than delta, and this is nothing but c minus delta less than x less than delta plus c. If I choose c satisfying this condition, this has to be true. This is what we would like to establish. Okay, so this should happen so that we can say it has the property of being uniform continuous. So let us mark that as equation 1. Okay, if we take delta to be equal to c, okay, this is a particular case, then the interval becomes what? Then the inequality in one at the interval becomes 0 comma 2 delta, right? Hence what happens in 1? Hence equation 1 must hold for any x in this interval, right? So whether this is being satisfied or not, this is what we are going to see. When we take some x which is very close to 0, then your c minus x upon cx approaches infinity, and hence your c minus x upon cx less than epsilon is not satisfied. So this will not be satisfied in this case. Here what happens? Only based on this, the uniform continuity tells you that it has to be true for all values in this interval, in the specified interval. We are not taking x equals 0, we are just taking x approaches 0, which means we are taking some value which is very close to 0, which is present in this interval. But when you choose x to be that such point, you get this goes to infinity and the requirements is not satisfied. Hence f of x, given f of x, that is 1 upon x, where x takes the values in the open at 0 closed at 1 interval, is not uniformly continuous. You might be wondering, in this interval this function is continuous but it is not uniformly continuous. Why? Let me tell you, this is the fact that when your x approaches 0, your value grows anonymously. To be precise, this function is not defined at the point when x is 0, right? And that is why uniform continuity is not taking place over there. Using some diagrammatic representation would have given you, when your x is 1, you get your function value to be 1. When your x is 2, sorry, okay, this is where oh, again, sorry, so this is going to be somewhat like this, right? So when it is getting near 0, it will go very close to this axis, and this is gonna happen. If you choose a very small distance in the x-axis and look for the corresponding changes in the axis, that is going to be very huge in this context. Uniform continuity does not take place. Okay, but the function is there without any break. That is why it is continuous. Fine. Here, the delta value, whatever may be the epsilon that you choose, whatever may be the epsilon that you choose, you can always find some delta based on the point and the epsilon value to satisfy the requirement of continuity. Here you will have to choose your delta value only based on epsilon, which means epsilon is some negligible quantity, delta is some negligible quantity, which is chosen only based on epsilon. In this case, there will be a tremendous difference in the function values. Like even this is considered to be a tremendous one when epsilon and delta are considered, right? This problem, this 1 upon x, a natural question may arise in our mind that this 1 upon x is not uniformly continuous on any interval. That is not so. Let me make it as a remark. Okay, 1 upon x is uniformly continuous on a comma infinity for some a positive. If you choose a to be any positive value, okay, this is gonna happen. This function is uniformly continuous, and hence, of course, whenever a function is uniformly continuous, it is also continuous. Now let us go to the next problem and have a look at it quickly. The next function that we are going to consider is f of x is x squared on the interval minus 1 comma 1. Okay, let us choose any 2 points in this interval. Let me check what is f of x1 minus what is f of x2, and this value happens to be x1 square minus x2 square. Using some standard results in algebra, we may write this as absolute of x1 minus x2 times of x1 plus x2. Okay, and this quantity has to be less than epsilon, and we'll have to identify some x1 minus x2 thing, right? So when you choose your absolute of x1 minus x2 is less than half times of epsilon, this is gonna happen. Okay, so this quantity half times of epsilon, we take it as delta. Here, if you see, whatever may be the points that you choose as x1 and x2, this can happen, and that is why we conclude that this function is uniformly continuous. Okay, you just multiply x1 with this and x2 with this, and you can see things happening smoothly, right? And the next problem, I am not going to prove this, so let me just state the things. F of x is sine x. This is uniformly continuous on the non-negative real line. Okay, and let me give you another example, that is f of x is sine x square is not uniformly continuous on the same interval. Closed at 0, open at infinity. Okay, I rest the examples here, and if you have any doubts on trying these things, you may always post it in the comment section. That will be clarified. Thank you.